Lecture on Chapter 4. Today we are going to cover the dissolving process as well as net ionic equations. So first we need to talk a little bit about solutions in general. So an aqueous solution is formed when a solute is dissolved in water. And this is really important that it's being dissolved in water. Water here is our solvent, so that's why we call it an aqueous solution. If it was dissolved in something else, we could still call it a solution, but it wouldn't be an aqueous solution. So we use this word aqueous to imply that it's dissolved in specifically water. So if we think about two really familiar aqueous solutions, we have salt water and sugar water. Salt water is a homogeneous mixture of sodium chloride and water, right? It's a homogeneous mixture because we can't see those individual salt pieces that are being dissolved. Sugar water would look exactly the same. Sugar water is a homogeneous mixture of sugar and water. And as you stir either one of those two substances, right, it seems to disappear. And so we're going to talk just really briefly about how these two different solids dissolve in water. So there are really strong attractive forces that are between the solute particles that hold them together. And we're going to talk more about this later in the course. But the solute, right, and the solute, that's what's being dissolved. And so we have these really strong solute-solute interactions, right? We have ionic bonds or covalent bonds, right, where the attractive force is holding them together. But there are also attractive forces between the solvent molecules, right? Between the water molecules. That'll actually be hydrogen bonding that we'll talk about again a little later. So we have really strong attractions between the solute particles, really strong attractions between the solvent particles. And when we mix the solute and the solvent, there are attractive forces between those, these solvent-solute interactions. And if those interactions between, right, like the water and the salt or the water and the sugar, if those attractions are strong enough, then that solute will dissolve. So we need the solvent-solute interactions to be strong enough to overcome the solvent-solvent interactions and the solute-solute interactions. So here is what it looks like when sodium chloride dissolves in water. We have these little purple cations, so these are sodium, and we have the large anions, those will be the chlorides. And what happens is that these water molecules get close to the salt crystals and they will pull off pieces and then surround them. You'll notice that the water molecules, right, those ones that look like Mickey Mouse ears, the white ones, those are hydrogens, and the red ones are the oxygens. And water is shaped like this. Okay, and so it's a bent molecule. That's why these are showing as bent. So the oxygens end up getting a partial negative charge in this molecule, and the hydrogens will end up getting a partial positive charge because the oxygen is more electronegative than the hydrogen. It will pull some of the electrons in the bond closer to the oxygen, making it have this partial negative. So this partial negative on oxygen is attracted to the positive, sodium atoms, so sodium ions. So we have these sodium ions, when they get dissolved, the water molecules will orient themselves so that the negative oxygen is next to the positive ion. And the same thing is true for the chloride. The chloride is negatively charged, so the water molecules will orient themselves so that those partial positively charged hydrogens will be toward the negatively charged chloride. And that's why you'll see as this chloride is getting pulled off here, we have the positive hydrogens, or those partial positive hydrogens, doing the pulling off, right? We don't see the water molecule with the partial negative oxygen next to that chloride. We have it with the partial positive hydrogen, so they'll pull off each individual ion and then they will surround it by the water. And that's how we hydrate this salt crystal. Sugar also gets dissolved, right? But sugar doesn't break apart. As you'll see, sodium chloride is breaking apart into individual ions because it's an ionic compound. Sugar, though, is a covalent molecule, right? It's held together by molecular bonds, and these are not going to break apart in water, but we can dissolve the sugar molecule as a whole. Okay, so again though, the water molecules are going to orient themselves so that those partial positive hydrogens are oriented toward any negative oxygens, right, or partial negative oxygens. Same thing here, if we have our partial negative oxygen, it will orient itself toward a partial positive hydrogen. But again, it's not breaking apart into individual pieces, and as you look over in this picture on the right, the sugar molecules stay together because it's a covalently bound molecule, whereas ionic compounds will break into their individual ions. So that's how these two substances differ when they are being dissolved in water. We can also tell whether something is an ionic compound or not, right? Whether it's an ionic compound or a covalent molecule by dissolving it in water. So here, if we have just distilled water over here, or deionized water, and we try to run electricity through this water, it will not conduct electricity because there are no flowing ions, right? Nothing in this water molecule is charged. We have partial charges, right? We have like a partial negative on the oxygen and a partial positive on the hydrogen, but they're not actually charged. So distilled water or deionized water will not conduct a current. If we look in the second picture, we have salt, right? And we've stuck our electrodes in the salt. Salt by itself also will not conduct electricity because we don't have, free ions. We don't have ions that can cause electricity to flow. They're all bound up in this salt crystal. So if we try and run a current through just salt by itself, then, nothing will flow. But if we have an aqueous ionic solution, right? If we take our salt and we dissolve it in our water, now our ions are free and electricity can flow through this salt water. Okay, so we need free ions in order to allow electricity to flow. This is one way we can tell, sugar water apart from salt water. If we have sugar water, then we have no free ions, right? Nothing in here is charged, and therefore it won't conduct an electric current. But if we have salt water does have free charges and it can allow electricity to flow. So we could tell whether something was salt water or sugar water by sending an electric current through it. Just as a quick kind of interesting bit, I'm sure you've heard you're not supposed to, drop a hairdryer in a bathtub. And this is because, right, your tap water at home has ions in it. Right? Your tap water from your faucet has things like, calcium, it may have chlorides, it may have fluorides, it may have lead, it may have, a bunch of different things, but it has ions in it. And so your tap water at home is not just water, it's not pure water, it has ions. So that's why the tap water will conduct an electric current. You need to make sure to keep any electronics away from, your bathtub. Theoretically, if we filled our bathtub with completely distilled water, deionized water, it wouldn't have any free electron or any free ions in it, right? And it wouldn't conduct electricity. So theoretically, right, you would be safe if you, had a hairdryer in a bathtub full of deionized water. That being said, don't do that. But it is interesting. And you can do this experiment with the electrode in the lab. Again, don't try that at home with a hairdryer in your bathtub. Okay, I've talked about these before. These are our solubility rules for ionic compounds in water. So the way that we read this is that everything over here, right, if you see an ionic compound with one of these ions in it, then your compound is typically soluble, right, which means that it will form an aqueous solution. It will break apart into its ions if you put it into water. And then on this side, these are the exceptions. So if you'll look, lithium, sodium, potassium, and ammonium do not have any exceptions. That means that they are always going to be soluble. So if you see something with sodium in it, then it will always be soluble, always, always, always. Same thing with nitrate and acetate. If you see something with a chloride, right, or a bromide or an iodide, they are typically soluble. However, they do have some exceptions. So if you see a chloride with silver or mercury or lead, right, and specifically those ions of them, then they are insoluble. So like silver chloride is an insoluble compound, right? This will form a solid in our solution. It will not be an aqueous solution. So this is how we read this, right? Sulfate is going to be pretty much always soluble except when it's paired with strontium, barium, lead, silver, or calcium, right? Then it's going to be insoluble. The second half of the table shows ones that are generally insoluble. So like hydroxide and sulfide are typically insoluble except when it's, got all of these things. Okay. If they are paired with lithium, sodium, potassium, or ammonium, that was our first rule up here, then it's going to be soluble, right? And then sulfide and hydroxide have slightly different, right? If we have a sulfide with calcium, strontium, or barium, then it's going to be soluble. When hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble. We're typically going to treat that as soluble in this class. And then we have our carbonate and phosphate, again, mostly insoluble, but if it's with lithium, sodium, potassium, or ammonium, then it is soluble. You need to have these memorized for this class. We're going to do a lot with aqueous solutions, especially in this particular lecture and when we talk about molarity of leftover ions. But you do need to know these because we're going to write a lot of equations and you need to have them memorized. Okay. Double replacement reactions. We've talked about these before, and this is when the ions of two compounds exchange places. So here, the X and the Y are switching out, right? And so now, instead of A being bonded to X, A will be bonded to Y, and instead of B being bonded to Y, B will be with X. Okay, so there are switching spots, and we will form two new compounds in these double displacement reactions. This is how we are going to do these net ionic equations, because what happens is that one of the compounds formed is usually a precipitate, right, which means a solid, an insoluble gas that you'll see kind of try and bubble up, or you may make a molecular compound, which is usually water, and that will typically be in an acid-base reaction. So we have, if we form one of those three things, then we can write a net ionic equation for a reaction, which is showing the actual reaction that's happening. Okay, but this is the whole point of doing a double displacement reaction or double replacement reaction, is we're forming one of these three things. So there are a couple different types of equations that we can write for these aqueous ionic reactions. The first one is the one that you're used to. That's the molecular equation. It shows all of the reactants and products intact as undissociated compounds. We're just writing them just like normal. Another way that we can write it is the complete ionic equation. And in the complete ionic equation, we break apart all of our ionic substances. So anything that is ionic and soluble will dissociate into ions. So that's the trick here, right? It needs to be ionic and soluble. And then our last type of equation will be the net ionic equation. And this will show the reaction that's actually happening. It says that it eliminates the spectator ions. And the spectator ions are things that don't react. They are watching the reaction happen. They're kind of sitting off to the side. And the way that you'll see or that you'll notice these spectator ions is that they will stay the same on both sides. Like Na plus will be Na plus on both sides of the equation because it is always going to be soluble. And we'll get quite a bit of examples for this. So here's an example of a precipitation reaction. On the right here, or sorry, on the left here, this clear one, this is silver nitrate, which is really cool, actually. If you get it on your skin, it will actually turn black in the sunlight because it's photoreactive, right? It will cause your hand to essentially develop. It used to be used to develop photographs. So if you get, a dot of it or so on your hand, then it will develop in the sunlight and it will turn black. Obviously, you don't want to get silver on your hand as much as you can, but it is kind of cool. And then the one on the right, that yellow solution, that is sodium chromate. Okay, so both of these are going to form aqueous solutions because anything with nitrate is soluble and anything with sodium is soluble. So that's why they are both dissolved. When we cause this reaction to happen, right, we are going to form two different things. We are going to form sodium nitrate and silver chromate. Sodium nitrate, both sodium and nitrate are always soluble, so that's what's dissolved. That's floating around up here. This is sodium and this is nitrate. But silver chromate forms a solid. It is not a soluble substance. And so we have down here, this is silver chromate at the bottom, forming a solid. And that's what this red powder is down here. So sodium nitrate would stay up here in the solution, and silver chromate would be down as a solid. And so today we're going to look at writing reactions for these types of reactions. Okay, so here is the molecular equation. The molecular equation shows the total reaction that's going to happen. Silver nitrate reacts with sodium chromate to form silver chromate and sodium nitrate. You'll notice we have the states of matter, right? We have our aqueous for all of our solutions, and then the S for the solid precipitate that formed. We have balanced our equation, right? And we're showing everything in its regular molecular form. We can then write the total ionic equation, which will break apart any of the ionic compounds that are soluble. So you'll see silver nitrate breaks apart into silver and nitrate. And I want to point out that there was this 2 in the front. And when we have that 2 in the front and then we break apart silver nitrate, the 2 is going to go to the silver and to the nitrate, because that, if we had 1 silver nitrate, it would break into 1 silver and 1 nitrate, but we have 2 silver nitrates, so we get 2 silvers and 2 nitrates. Sodium chromate will break apart because it is aqueous, and when it does, the subscript 2 that was used to balance out the charge of the chromate will actually end up on the front of the sodium. So remember that 2 got there because we needed 2 Na pluses to balance out our CrO4 2 minus. So we have 2 sodium, so when this breaks apart, that 2 comes out front on the sodium, and then, chromate just goes back to being chromate. Silver chromate, we do not break apart because it is a solid. Okay, you do not break out solids, pure liquids, or gases, or molecular compounds. Those are the 4 things that stay together: solids, pure liquids, gases, and molecular compounds. So here we have a solid, we leave it together in our molecular equation. And then our sodium nitrate gets broken apart, again, 2 sodiums and 2 nitrates. Then we can go through and we can write our net ionic equation. And the net ionic equation is going to show the actual reaction that happens. And so the way that you're going to do this is you're going to look and see what shows up the same on both sides. So if you'll look here, we have 2 Na pluses on this side, and we have 2 Na pluses on this side. The sodium did not change from the left to the right. That is a spectator ion. It ends up in solution no matter on which side of the reaction it is. So we are not going to include it down in the net ionic equation. And then you'll notice we have 2 nitrates on each side, even though I've crossed it out down here. But we have 2 nitrates on each side. That is another spectator ion. It does not end up changing on either side of the reaction. So it will not show up in our net ionic equation. You'll keep including it in the total ionic, but we won't include it in the net ionic equation. So to get the net ionic equation, we're just removing any spectator ions from the total ionic equation. So we'll end up with silver plus chromate gives us silver chromate, and that's what's down here. Silver plus chromate gives us silver chromate. An easy way to write the net ionic equation, once you get really good at this, is to see what solid forms, and then you can actually kind of write it backwards and just break it into pieces, right? Silver chromate breaks into chromate and 2 silvers. Or you can go through this whole process and write the total ionic, see the spectator ions, the net ionic. Either way, it should work out just fine. Let's do another example. So this is lead 2 nitrate plus potassium iodide gives lead 2 iodide and potassium nitrate. So the first step would be to write the molecular equation. And then you're going to write the total ionic and the net ionic. If you'd like to give this a try, go ahead and pause here and try to do this yourself. And then you can come back and see the answer. If you're still not sure, then I would try and pause and at least do the molecular equation from, we've already covered nomenclature and we've covered balancing reactions, so I would try that. But otherwise, like I said, just come back when you're ready. Okay, so the first step will be to write our regular molecular equation. So we have lead 2, which means that lead is a 2 plus and nitrate is a 1 minus, right? So we'll write lead 2 nitrate. We have potassium iodide, K plus and I minus, and then we have lead 2 iodide, Pb2 plus and I minus, and we have K plus and NO3 minus. So we can go through and write our equation for this, right? Doing all of our bonding, and then we go through and we can balance our chemical reaction. So we should already know how to do this first step. The second step and the third step are what's new, right? Writing our complete ionic equation, we are going to break apart anything that's aqueous. So the reason lead nitrate was aqueous, right, is because nitrates are always soluble. So that's why it got an aqueous. Same thing with potassium. Potassium is always soluble, so that got an aqueous as well. Lead iodide, right, iodines are not soluble when they are bonded with lead 2, so that's why this is a solid. And then potassium and nitrate are both always aqueous, so that's how we got aqueous here. So now to write our complete ionic equation, we are going to break apart anything that's aqueous. So our lead will break into lead and 2 nitrates, right? So this 2 tells us that there are 2 nitrates, so that 2 will end up out front here, okay? And then we have our 2 iodides, or our 2 potassium iodides, so that 2 will go to the potassium and the iodine. Then we leave together PbI2, right? And then we have 2 potassiums and 2 nitrates. So that's how we're getting this complete ionic equation. Then we'll go through and we'll look for our spectator ions. And those are the ones, again, that are watching the reaction happen. They are showing up the same on both sides. So we have nitrates on both sides, and we have potassium on both sides. So those will end up getting eliminated in our net ionic equation. So our net ionic equation has Pb2 plus 2I minus gives us PbI2 as our solid. Again, those are things that are changing on either side of the reaction, and they're showing how that solid is being formed. So I want you to go ahead and pause here and do these 2 practice problems. Okay, I have 2 different examples of solutions that we would mix, and I want you to write the molecular equation, the complete ionic equation, and then the net ionic equation for each one. If you end up with stuff that is aqueous on both sides, so that's what this is here. It says if a reaction does occur, and the way that we would see that it doesn't occur is when all of our reactants and all of our products end up aqueous. If we're not forming a solid, a liquid, a gas, or a molecular compound, right? If everything is an ionic, aqueous substance on both sides of the reaction, then a reaction does not occur, in which case you'll just write the molecular equation and the complete ionic equation, and then you can't write a net ionic, you'll write the molecular and the complete ionic, but we can't write a net ionic equation because there's nothing that's actually being formed. Anyway, go ahead, go through this process, and then once you're ready, come back and I will give you the answers. Okay, so for the first one, we have sodium sulfate and strontium nitrate. So we have sodium is Na plus, and sulfate is SO42 minus, and we have strontium is Sr2 plus, and nitrate is NO3 minus. So the first thing that we need to do is write that molecular equation. So we have sodium sulfate, Na2SO4, right? And that's going to be aqueous because all sodium salts are aqueous. And then we're going to have strontium nitrate. And again, strontium nitrate is going to be aqueous because anything with nitrate is always aqueous. So now when we write our products, I like to think of the metals switching. So I'm going to switch sodium and strontium. So I'm going to end up with strontium sulfate and sodium nitrate. So strontium sulfate, that is going to form a solid. It's soluble, but sulfates are typically soluble, but strontium is one of the exceptions. So strontium sulfate is going to form a solid. And then we have sodium nitrate. And anything with sodium and anything with nitrate is always going to be aqueous, so that is really aqueous. And then we need to go ahead and balance our equation. Don't forget to balance it or it's not going to work out correctly. So that would be our molecular equation. Then we need to go through and write our complete ionic equation, which is going to break apart anything that is aqueous. So this sodium sulfate will break into 2 Na plus and SO4 2 minus, and then our strontium will break apart and we will get 2 nitrates, right? Because that 2's got to pop out front. And then we are going to get our strontium sulfate solid. Do not break apart strontium sulfate because it forms a solid. Then I'm going to continue on below here, and then we'll get 2 Na plus and 2 nitrates. So that would be our complete ionic equation. We have broken apart anything that is aqueous. So now when we write our spectator or our net ionic equation, we need to eliminate our spectator ions. So our spectator ions are going to be sodium and nitrate, because those are the ones that show up the same on both sides of the reaction. So then we can go ahead and write our net ionic equation, which is our sulfate reacts with our strontium and forms strontium sulfate. All right, so that's the molecular, the total ionic, and the net ionic equation for this reaction. Let's try the next one. So this is ammonium perchlorate and sodium bromide. So we have ammonium is NH4 plus, perchlorate is ClO4 minus, and then we have sodium and bromide. Okay, so now we can go ahead, we can write our molecular equation. So we have NH4, ClO4. Anything with ammonium is always going to be soluble. Also, most perchlorates are soluble. If you look at the solubility rules for ionic compounds that is on Canvas, you have more solubility rules down at the bottom, and they're the ones that say helpful to know. Those are ones you don't have to have memorized, but they do help when you're working with things that, don't follow the rules that you have to memorize. Anyways, this is aqueous because ammonium's aqueous. And then we have sodium bromide, which is aqueous. And then that's going to form, right, we are doing our double replacement reaction. We're going to get ammonium bromide, which is going to be aqueous because it has ammonium. And we're going to get sodium perchlorate, which is going to be aqueous because it has sodium. So you'll notice, though, everything is aqueous. This means that no reaction is actually happening. We just poured together 2 solutions, and they just kind of sat in there. So we can write our complete ionic equation because this is what's going to be floating around in solution. We're going to break apart all of these compounds, and it's all of them because they are all aqueous. So just go through, break apart everything, and it was already balanced, so we didn't need to add any coefficients or anything. So we can just break it all apart. All right, so now when it asks for a net ionic equation out of this, we can't write a net ionic equation because there's no reaction that's actually happening. So we would just write no reaction. Okay, those are our 2 examples. So this is kind of how we do, kind of regular problems where a solid is being formed or no reaction is occurring. We also have some special things that happen, like we have acids and bases. So we have acids and bases that react a little bit differently in water. And so we'll go through those, but first you need to know your acids and bases. There are a series of strong acids. You need to have these memorized. Okay, so we have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. Those are strong acids. You need to memorize those. The weak acids are going to be anything that is not a strong acid. So we have some examples here: hydrofluoric acid, phosphoric acid, and acetic acid. And I include these three because these three are the ones that people typically think are strong acids. The hydrofluoric acid is actually one of the strongest weak acids, but it is a weak acid. And the reason that people get it mixed up is because all of these other binary acids up here, those are all strong acids, but hydrofluoric is a binary acid that is a weak acid. And then phosphoric acid people always think is strong for some reason, and acetic acid you will see a lot. Those are the two different ways you can write it, but it is a weak acid. But like I said, memorize the strong acids, and then any other acid you come across will be a weak acid. Strong bases are easy to recognize because it will be anything that has an OH, right? So we've got sodium hydroxide, potassium hydroxide, calcium, right? There's just a bunch of hydroxides, anything with OH minus. And then weak bases, we're not going to deal with a ton. The only weak base that we're going to deal with is ammonia. But weak bases in general typically contain nitrogen. You'll get more into this in Chem 2. And the reason that we care if we have, strong acids or weak acids or strong bases or weak bases is because strong acids and bases, these guys will break apart. These we will treat as ionic compounds when we are doing these reactions. And weak acids and bases we will typically treat as molecular compounds. So strong acids and bases will ionize completely in water, which is why we treat them like ionic compounds, whereas weak acids and bases don't ionize completely. They might only ionize like 5%, so we will treat them as molecular compounds when we're writing these net ionic equations. So you need to know whether your acid is strong or weak or your base is strong or weak so that you write these reactions correctly. So let's try this. So remember our general rule, if we have an acid plus a base, then we are getting a salt and water. And remember that a salt is another word for ionic compound. It doesn't mean that we're making sodium chloride. We might, but it just means that we're making an ionic compound. So here's our problem. This says write a balanced molecular, total ionic, and net ionic equation for the following acid-base reaction and identify the spectator ions. And my hint here is that strong acids and bases ionize in water, right? Like ionic compounds. So first thing we'll do is we'll write out the reaction. Strontium hydroxide plus perchloric acid. Okay, so if we have strontium hydroxide reacts with, we need our aqueous in there, reacts with perchloric acid, and both of those are going to be aqueous, not only because it says it, right, but because, we have our hydroxides are typically insoluble, but strontium is an exception. And then perchloric acid, most perchlorates are soluble. And then when we react those together, right, one of the things we're going to get is water. And whenever you're writing water, it's always going to get an L. Water is a pure liquid. And what this means practically is that when we are writing these ionic reactions, this either complete ionic or this net ionic, we are not going to break apart water because it's a pure liquid. The other thing that we're going to get is we're going to get strontium perchlorate. And that is going to be aqueous because perchlorates are typically aqueous. Okay, so now we can go through and we can balance our equation. And then we can go about writing our our complete ionic equation. Again, we will break apart anything that is aqueous. So we'll break apart strontium and hydroxide. Remember that 2 is going to go out front. We'll break apart our perchloric acid. And again, that 2 will get distributed to the hydrogen and to the perchlorate. And then water will stay together because it is a pure liquid. So don't break apart the water. And then we've also got our strontium and our perchlorate. Okay, so now we'll go through and we'll look, and eliminate all of our spectator ions. So strontium is our spectator ion because it stays the same on both sides. Same as the perchlorate, it stays the same on both sides. So we've only got our hydroxide reacting with our hydrogen to produce water. You'll notice that all of those have a 2 in the front. And since all of those have a 2 in the front, we will actually reduce it when we go and write our net ionic equation. So our net ionic equation is going to be our hydroxide plus our hydrogen gives us water. And this will always actually be the net ionic equation when we have a strong base and a strong acid. If both of them are strong, this will always be our net ionic equation, just based on what they are. Our hydroxides will always break apart into hydroxide. Our acids will always break apart into H+, and they will always react together to form water. But only with strong acid plus strong base. If either one of those is weak, then that's not true. But this is the thing, water is a molecular compound, so don't break apart the water. So now let's look and see what it looks like with a weak acid. So our example here is that sodium hydroxide is reacting with aqueous acetic acid. So our sodium hydroxide, right, is reacting with aqueous acetic acid. And when these react together, we'll get sodium acetate, right? The sodium will end up with the acetate. And the H and the OH will react to form water. So this is very similar, or it looks very similar to our last problem, right? Where we have an acid and a base, and we got a salt and water. But the thing that's different is that we are using a weak acid instead of a strong acid. So this will look different when we write out our complete ionic and our net ionic equations. So our complete ionic equation will look like this. So we'll have our sodium plus our hydroxide. And then this weak acid, we do not break apart. Weak acids and bases do not ionize in solution, so you're going to leave them together. So we'll just get our acetic acid just the same. And then we'll break apart our sodium acetate. And then again, we don't break apart water. So now we look and we see, okay, what's the same on both sides? So we have sodium stays together on both sides, but as you'll see, the acetate, right, on the left side, it's acetic acid, and on the right side, it's acetate. So it changed. So we can't cross out the sodium or the acetate because it changes. So the only spectator ion in this reaction was our sodium. So now we can go through and write our net ionic equation, which is now a little bit longer than we have been seeing because so many things are being changed from one side of the reaction to the other. So we keep our acetate and our water. So that is our net ionic equation for this reaction, right? When we have a weak acid plus a strong base. The strong base broke apart, but the weak acid did not. We still formed a salt and water, but here we have our anion then and our water. Okay, so now we covered weak acids. Let's go ahead and look at weak bases. Weak bases, we're typically going to use ammonia, and it will sometimes show up, you'll see it written as ammonium hydroxide. And this is just hydrated ammonia, which is typically how we see ammonia anyways. So whenever you see ammonia, so like if it tells you ammonia is reacting, you're always going to write it one of two ways. You can write it like this, where we have ammonia plus water, or you can write it as ammonium hydroxide. So it's going to tell you ammonia, and you're going to write it either as ammonia plus water or as ammonium hydroxide. Just so you know, typically I will write it as ammonium hydroxide in the molecular equation because it's easier for me to see what the products are, like what is going to be formed during the reaction. When you write it as the net ionic equation, you don't have an option. You must write it like this, or sorry, as the complete ionic equation. So in the molecular equation, you can write it either way. Like I said, I will usually use ammonium hydroxide in my molecular equation. And then you must write it like this, though, when you break it apart. When you break it into, for that complete ionic or the net ionic equation. And the reason I'm stressing this is because people will see ammonium hydroxide and they're like, ah, that's going to break apart into ammonium and hydroxide. And it's a base, right? No, that will cause you to write a totally different reaction, because remember, the only reason we're writing it as ammonium hydroxide is because it's hydrated ammonia. It's actually ammonia and water. So be very careful, don't do this, okay? So our example here is if we have ammonia reacting with hydrochloric acid, we can write it like this. We can write ammonia plus water, right? Again, anytime you see ammonia, add the water in there, plus our hydrochloric acid will give you ammonium chloride and water. Or you can write it as this. Okay, so we have ammonium hydroxide, right? Our hydrated ammonia plus hydrochloric acid gives you ammonium chloride and water. So again, I like to write it this way for the molecular equation, because then I can really clearly see, oh, this and this are going to form water, and ammonium and chlorine are going to form my salt. So it's really easy to see that way what our products are. Just again, the hazard is that when people start breaking this apart, they need to break it into this, not this, okay? So let's go ahead and try one. So this says, our example here is ammonium hydroxide is reacting with magnesium chloride, and it wants the balanced molecular, total ionic, and net ionic equations for the reaction. So first off, we need to write our reaction. So we have ammonium hydroxide, and that's going to react with magnesium chloride to form ammonium chloride, which is going to be aqueous because it has ammonium, plus magnesium hydroxide, which is going to be a solid because most hydroxides form solids, and that's not one of the exceptions. So then we can go through and we can balance our equation, and we're good to go there. So then we will write the net ionic equation. So in the net ionic equation, again, people will see ammonium hydroxide and they'll break it into ammonium and hydroxide. Don't do that. You're going to write this as ammonia and water. Okay, so we'll get two ammonias. And actually, our ammonias are going to be a gas in these reactions. And then we'll have water, which is a pure liquid. And then we'll get our magnesium and our chlorine. And then we'll break this apart, right? Our ammonium and our chloride. And then we will leave together our magnesium hydroxide salt. So then again, we need to see what is the same on both sides. So as you'll see, ammonia changes to be ammonium, so that's different. So that's why it's really important to break this apart correctly. If we had broken it apart into ammonium and hydroxide, we would actually end up canceling it out right here, and we would write the incorrect complete ionic equation. Okay, so we need to write it as ammonia and water so that the ammonia can turn into ammonium during the reaction. Everything else stays the same except for these chlorides. The chlorides are the only ones that end up being the same on both sides. So then our our net ionic equation, we have our ammonia gas plus our water and our magnesium gives us our ammonium. Sorry, I missed a 2 up here in front of water a while back. Will give us our ammonium and our magnesium hydroxide. Okay, so again, the thing people do wrong here is that they split up that ammonium hydroxide incorrectly. So just keep that in mind as like something you need to remember. And then our last type of way that this can show up is if we have a gas evolution reaction. And so this is when, like, we have our reaction up here. We have sodium bicarbonate and hydrochloric acid is going to form water, sodium chloride, and carbon dioxide, which is a gas. Essentially what happens in the lab, we pour together some our hydrochloric acid and sodium bicarbonate, and we get bubbles. That's what it would look like. It starts bubbling. And those bubbles are carbon dioxide. Okay, this is essentially an acid-base reaction. We have our acid, and then this is a basic anion. And so we're getting an acid and a base. We're forming a water and a salt and a gas. Okay, So we'll still end up with a pure liquid, right? Our water will end up with a dissolved salt, but we're also getting gas that's bubbling. So again, like I was saying earlier, we're never going to break apart liquids, gases, solids, and molecular compounds. So here, this is how we're going to see how to write it for the gases. There are 3 different gases that you really need to look out for that are being formed. We've already talked about ammonium down at the bottom, or ammonia. So that's here. But the other 3 gases you need to keep an eye on, if they're being formed, they'll come from carbonic acid, sulfurous acid, or even just if you form H2S. Okay, so if you form H2S, then that is always going to be written as a gas. If you form carbonic acid, right, so say you were going to write a reaction and you're going to form H2CO3. You're going to think of that as, oh no, I can't write that as H2CO3 because it actually breaks down in water, and it will be instead water and carbon dioxide. Again, water is going to be a pure liquid, and our carbon dioxide is going to be a gas. So if you were ever going to write carbonic acid as a product, you're not going to write it as a product. Instead, you're going to write water and carbon dioxide. Same thing, if you were going to form sulfurous acid, H2SO3, then you're like, nope, not going to write it as that. I'm going to write it as water and sulfur dioxide. Okay, again, water is pure liquid. Sulfur dioxide is a gas. Okay, so let's go ahead and we'll see an example of how this might occur. So here we have nitric acid reacting with aqueous sodium carbonate. So we have nitric acid reacting with aqueous sodium carbonate, and that will form sodium nitrate, right? We have nitrate and sodium, so we'll get sodium nitrate, which will be aqueous, and then we'll get our hydrogen and our carbonate, which would form H2CO3, carbonic acid. But I told you can't write it as carbonic acid. Instead, we're going to write it as water and carbon dioxide. Okay, so you need to keep an eye out for that being formed. Then we need to go through and we'll balance our equation before we move forward. Okay, so don't write carbonic acid, write water and carbon dioxide. Then again, we'll do just the same as we normally do. We'll break apart our strong acid over here, right? Nitrate is a strong acid, so it breaks apart. Then we have our sodium carbonate, which is aqueous. Then we have sodium nitrate, which is aqueous because anything with sodium or nitrate is aqueous. And then we have water, which is a pure liquid, so we can't break that apart. And we have carbon dioxide, which is a gas, so we can't break that apart. So we go through, we identify our spectator ions. We have nitrates on both sides, sodiums on both sides, so then we can write our total ionic equation as 2H plus CO3 2 minus gives us water and carbon dioxide gas. Okay, so like I said, just be careful. Otherwise, had we written this as 2H plus and CO3 2 minus, right, then you would try and cancel out that carbonate and the hydrogen, really, and nothing would happen. So we can't write it like that. If you come up with carbonic acid, you're going to write it as water and carbon dioxide. And like I said, the same if you come up with sulfurous acid, you're going to write it as water and sulfur dioxide. Okay, so that's how we do these gas-forming reactions. And that is the end of our net ionic equations and our lecture on solubility. I know it was a long lecture. Thanks for sticking with it. So now you need to go and practice writing these net ionic equations. There's a bunch of different ways that they show up, and you're going to really need to get some practice. You have some practice in your Chapter 4 lecture worksheet, but you also have a lab on writing net ionic equations, where you're going to get a lot of practice writing these net ionic equations. The answer key will be posted, so make sure you check your work and that you are doing it correctly. As always, if you have any questions, please send them to me. Otherwise, I will talk to you next time.